Hi everyone, and welcome back to the MCAT A series of lectures in physics. In the previous video, I gave a brief introduction to the idea of waves and the theory behind them. In this video, I shall focus in on one particular type of physical wave, that is, a sound wave. I shall begin this video by describing how sound waves are created, before then quantifying how fast they move in solids, liquids, and gases. Sound intensity will then be introduced, which quantifies how much energy is associated with a particular sound wave. Sound attenuation or damping will then be considered, which is simply the reduction of the amplitude of the sound wave. The change in frequency of a sound wave due to either the motion of the observer or the source will then be considered with the Doppler effect. How our ears distinguish different types of sound waves will then be discussed in relation to pitch. Standing waves will then be discussed with a particular focus on such waves in pipes and strings. Ultrasound, a very useful application of sound waves, will then be discussed in detail. I will then finish this video by discussing what happens when an object travels faster than the speed of sound in that medium, thereby creating what are known as shock waves. As I discussed in the previous video, sound waves are a type of longitudinal wave. That is, the direction of propagation of the wave is parallel to the direction of oscillation. The wave travels in the same direction it is oscillating. Sound waves are in fact created simply by the disturbance of particles within the medium. For example, if we consider a container of gas, then I can consider applying a force from the left to the right on that gas. Doing so is going to push some of those particles further to the right. In other words, we are going to have areas of low density and high density created by this mechanical disturbance. I can then repeat this process over and over, creating more and more compression and rarefaction regions. These alternating regions of different particle densities travel through the medium, allowing that sound wave to propagate. As sound waves are created by the disturbance of particles, they cannot exist in a vacuum. Particles need to be present in order for the sound wave to propagate. As we shall see in the next video, this is not a criterion for light waves. Light waves are a form of electromagnetic wave. They are an oscillation in the electromagnetic field and therefore do not need particles to be created and propagate. Again, sound waves are created in a medium due to a mechanical disturbance in that medium. Therefore, we would expect the speed of sound waves to be different in different media, and that is exactly what we get. The speed of sound in a particular medium is in fact given as follows. The speed of sound v is equal to the square root of capital B, which is known as the bulk modulus of that medium, divided by that medium's density rho. The bulk modulus B is simply a measure of that medium's resistance to compression, how difficult it is in a sense to squash the particles within the medium together, thereby creating sound waves. The larger the value of the bulk modulus, the larger the sound speed will be in that medium. Therefore, the bulk modulus is greatest in a solid and smallest in a gas. Conversely, the speed of sound increases as the density decreases. Overall, according to this equation, sound waves travel fastest through a solid and slowest through a gas. On the MCAT, the most common medium that appears is that of simply air. In air, the speed of sound is roughly 343 meters per second. Of course, as you may have guessed, the temperature of that gas is also important. Remember, temperature has to do with the average kinetic energy of the particles. Depending on how much the particles within the gas are bouncing around is going to change the speed of sound within that medium. Therefore, this value that I have presented, 343 meters per second, is true at approximately 20 degrees Celsius. Overall, the most important thing to remember so far is that the speed of sound is fastest in a solid with low density and is slowest in a gas of high density. In the previous Introduction to Wave Theory video, I introduced the idea of frequency. Frequency was defined as the number of cycles per second. In other words, how often or the rate at which a particle or wave completes a cycle. Our ear's perception of frequency is known as pitch. We say that a wave that has a low frequency also has a low pitch. Likewise, waves that have a high frequency instead have a high pitch. For example, this wave that I have drawn here has a low frequency. It is very spread out, and therefore the number of cycles per second is very small. Our ears will perceive this as a low-pitched sound. Conversely, this wave that I have drawn here has a high frequency. There are a lot more cycles in the same distance. This is a high-frequency wave, and therefore our ears will perceive this wave as a high-pitched sound. It is important to note here that our ears are not sensitive to all different frequencies. They are only sensitive to a frequency range. It turns out that for the average human, that ranges from 20 Hz to 20,000 Hz. Sound waves below 20 Hz and above 20,000 Hz will not be detected and therefore perceived by our ears. Waves with a frequency below 20 Hz are known as infrasonic waves, and above 20,000 Hz are known as ultrasonic waves. This, remember, is the frequency range for a human. Other living things have different frequency ranges. For example, a dog can perceive sound waves below 20 Hz, and that is how a dog whistle works. We cannot hear a dog whistle because our ears are not sensitive to that range. However, a dog can hear it because their ears are sensitive to frequencies below 20 Hz. On the other end of the spectrum, ultrasound machines operate at frequencies above that our ears can perceive, above that of 20,000 Hz. I shall go into more detail about ultrasound waves at the end of this video. Now I would like to move on to discuss what happens to the pitch or frequency if either the source or the observer is moving. I'm sure most, if not all of you, have noticed this effect known as the Doppler effect in your everyday lives. For example, if a fire truck or an ambulance passes you by, you will notice a distinct change in pitch when comparing that vehicle approaching you to that vehicle moving away from you. This is caused by a difference between the actual frequency emitted by that vehicle and the perceived frequency that reaches your ear. This is because the perceived frequency by our ear is dependent upon the speed at which that sound wave enters our ear. Remember, the speed of sound in air at 20 degrees Celsius is 343 meters per second, but if that sound wave is emitted by a moving object, or if the observer, in other words us, if we are moving, then we are also going to detect a different speed for that sound wave. This is going to, in a sense, change the perceived frequency of that sound wave. To make sure we understand this, let us consider a general example of both the source and the observer moving. Here, I've considered a vehicle emitting some sort of siren moving to the right. This sound wave is going to be detected by a human that is moving to the left. Let us denote the speed of sound as simply v, the speed of the source, in other words in this case the speed of the vehicle as v sub s, and the speed of the detector, in this case the human, as v sub d. For this general case, the perceived frequency f prime is given as follows. F prime is equal to f, where f is the actual emitted frequency, multiplied by a quantity that depends upon these three different speeds. It is multiplied by the speed of sound plus or minus the speed of the detector divided by that same speed of sound plus or minus the speed of the source. In general, this equation is telling us that if the source and detector are moving away from each other, then the perceived frequency is less than the actual frequency, and if the source and detector are moving towards each other, then the perceived frequency is instead greater than the actual frequency. Of course, we have to be careful here because there are four different possibilities. The source can either be moving away or towards the observer, and the observer can also be moving towards or away from the source. The sign convention here, and you must know this for the MCAT, is as follows. When the detector is moving towards the source, then V sub d is positive. When the detector is moving away from the source, Vd is negative. Instead, and it's important that you don't mix this up, when the source is moving towards the detector, Vs is negative. When it's moving away from the detector, Vs is positive. To check that we understand these sign rules, let us consider a simple example. Let us assume that we have an object emitting a sound and moving to the right towards a stationary observer. Let us assume that this object is moving with a speed of 140 meters per second. Again, as I stated, the observer or the detector is stationary and therefore it has no velocity associated with it. What is the perceived frequency in this case? What is the frequency detected by the ear of that detector, of that human? Well, let's recall the general formula. The perceived frequency f prime is equal to the emitted frequency f multiplied by the speed of sound v plus or minus the speed of the detector. However, here the speed of the detector is 0, so therefore I can just write down v divided by that same speed of sound plus or minus the speed of the source. Here, as the source is moving towards the detector, that speed of sound is going to be negative. We therefore have a minus v sub s. Plugging in the numbers, I haven't told you the frequency yet because I want to work this out in general. But the speed of sound I will take to simplify things as simply 340 rather than 343, divided by that same 340 minus the speed of the source, minus 140. Working this out, we get that the perceived frequency is 1.7 multiplied by the actual frequency, the frequency of the emitted sound wave. Therefore, we see that as that object is approaching the source, the perceived frequency and therefore the perceived pitch is greater than the actual frequency. We perceive a higher pitch than that is actually emitted from the source. Once that source has passed us, it is then going to start moving away from the detector, moving away from that human. We can then ask, what is the perceived frequency of the sound wave as that object is moving away from the detector? Again, we can use the same formula. F prime, the perceived frequency, is equal to the actual emitted frequency f, multiplied by, again, v plus or minus the speed of the detector, which again here is 0, so we just have v, divided by the same speed of sound, plus or minus the speed of the source. As the source is now moving away from the detector, the speed is taken as positive. We now have v plus v sub s on the denominator. Again, working this out, we get 340 divided by 340 plus 140, and working that out, it is roughly equal to 0.7 times the actual emitted frequency. As the source is moving away from the detector, the perceived frequency is less than the actual emitted frequency. Hopefully, this is what you have seen when you have heard a fire truck or an ambulance as it passes you. As, for example, an ambulance approaches you, you hear a very high pitch, and as it is moving away from you, you instead hear quite a low pitch. This is due to what you now know as the Doppler effect. We can now consider a very special case of the Doppler effect. What happens when the speed of the source is in fact greater than the speed of sound? What happens when v sub s is greater than v? To understand this, let us consider an object that is moving to the right at a speed greater than sound. Let us also assume that this object is continuously emitting sound waves as it moves. As this object is moving greater than the speed of sound, the sound waves that it emits are going to build up behind that object, as I have shown here. Recalling that sound waves are simply due to compression regions, this buildup of sound waves is going to create a large pressure gradient, a large buildup of particles over a small area. This very condensed area or wavefront is known as a shock wave. Again, as I stated, a shock wave creates regions of very high density of particles. These particles must have come from somewhere, and therefore the region next to a shock wave has a very low density, a very low pressure. Therefore, as a shockwave passes through a medium, it creates an area of very high pressure followed by an area of very low pressure. This is what is known as a sonic boom. It is important to note here a common misconception with sonic booms. A large portion of the general public believe that a sonic boom is only created as an object's speed goes from slower than the speed of sound to faster than the speed of sound. In other words, its speed exceeds Mach 1. Mach 1 is known as the speed of sound. However, based on what I just described, sonic booms always happen as long as that object is going faster than the speed of sound. It has nothing to do with passing this threshold, passing Mach 1. As long as the object is moving faster than the speed of sound, a sonic boom is created. Now I would like to consider what is known as sound intensity. Intensity is properly defined as power per area, but in terms of sound, we know it best as the loudness of the sound, how high the volume of that sound is. The volume of sound is determined by its intensity. Intensity can also be defined as the average rate of energy transfer per unit area. And therefore the intensity is also associated with the energy within each sound wave. For a particular sound wave of a particular amplitude, the intensity of that sound wave is in fact directly proportional to that amplitude squared. As I stated in terms of power, let us consider a source that is emitting sound waves with a power P. We can then ask, what is the sound intensity through a cross-sectional area capital A certain distance d away? This sound intensity capital I is simply equal to the power of those waves capital P divided by that cross-sectional area capital A. Also, as sound waves spread out from a point source, this sound intensity must also be inversely proportional to the distance from the source squared. Anytime you have a quantity spreading out from a point, that quantity is going to be inversely proportional to the distance from that point squared. Finally, as intensity is power per unit area, it has units of watts per meter squared. As with frequency, our ears cannot perceive sound waves of all intensities. In fact, the softest sound waves our ears can perceive has an intensity of approximately 1 multiplied by 10 to the minus 12 watts per meter squared. This quantity is known as the threshold of hearing. On the other end of the spectrum, any sound intensities greater than roughly 10 to the 4 watts per meter squared can typically cause permanent ear damage. That much power over such a small area is too much for the ear to handle. Note the difference in frequency range compared to intensity range. The perceived frequency is from 20 Hz to 20,000 Hz. However, the intensity range is from 10 to the minus 12 to 10 to the 4. As this is such a huge range, it makes sense to instead consider a logarithmic scale for sound intensity. This scale is known as sound level. For a particular sound intensity capital I, the sound level beta is given as follows. Beta is equal to 10 multiplied by the log of that sound intensity divided by that threshold of hearing 10 to the minus 12 watts per meter squared, which I will denote as I sub 0. I sub 0 is the threshold of hearing. It is the softest possible sound that can be detected by our ear. Sound level is instead measured in decibels, which is perhaps a unit you've heard of before. Hopefully you're not confused by what I just did. We have not introduced a new quantity associated with a sound wave. All we have done is considered the fact that sound intensity is over a very large range. We have therefore changed this linear scale with sound intensity to instead a logarithmic scale known as sound level. An example of a logarithmic scale you may have seen before is the pH scale. The pH scale, remember, is a measure of the acidity of a substance, but a substance that has a pH of say 12 is not twice as acidic as a substance which instead has a pH of 6. This is because this is a logarithmic scale. This is because the acidity of a substance is over such a large scale that we have replaced such a scale by the pH scale, which is instead logarithmic. If you do not feel you are comfortable with using logs, don't worry, I will consider a question at the end of this video dealing with sound level. I would now like to describe what happens when two waves interact with each other, in other words, interfere with each other. This interference is fully described by what is known as the principle of superposition. According to this principle, when two waves interact with each other, the resultant wave that is created has displacements that are simply equal to the sum of the displacements of the two interacting waves. For example, we can consider the two waves I have drawn here, this blue wave and this red wave. According to the principle of superposition, these two waves interacting or interfering with each other creates the resulting wave as shown. The displacements of both the blue and red wave simply sum up to create the displacements of this resultant wave. As a special example, we can consider two waves that are completely out of phase with each other. Remember, being completely out of phase means that the antinodes of one wave overlaps with the nodes of another wave, as I have drawn here. When two waves are out of phase with each other, such as this, the amplitude of the resulting wave is simply the difference between the amplitudes of each individual wave. In the very special case of both waves having the same amplitude, this means that these waves in a sense cancel each other out. They create a resultant wave with no amplitude. This is known as destructive interference. On the other hand, if two waves are in phase with each other, in other words their nodes and antinodes overlap, then the amplitude of the resulting wave is simply equal to the sum of the amplitudes of each individual wave. For example, these two waves here are in phase with each other and therefore create a resultant wave that has an amplitude equal to the sum of the amplitudes of each individual wave. Based on this idea of wave interference, I would now like to consider a special branch of waves known as standing waves. To understand how such waves are created, consider the following situation. Let's assume that we have a string that's fixed at one end, for example tied to a wall, and we are holding the other end with our hand. We can then consider oscillating that string vertically with our hand. Doing so is going to create a wave that propagates towards the wall, towards the other end of the string. Once that wave hits the other end, it will then be reflected and head back towards my hand. If I continue to oscillate the string with my hand, then I can create another wave that travels toward that reflected wave. Naturally, therefore, these two waves can then interfere with each other. If I have oscillated the string at the correct particular frequency, these two waves will interact with each other in such a way that a standing wave is created, a wave that appears to be stationary on the string. As an example, let us consider the following setup of a standing wave. Again, on the right we have a wall, and on the left we can either have my hand oscillating or we can have another wall. In the latter case, the string can be oscillating because of a machine that is moving that string up and down on the left or right. This standing wave that I've created is in fact the simplest possible standing wave. The ends of the string do not move, and the rest of the string is apparently moving up and down. The points on the string where it is not moving are known as nodes, and the points halfway between the nodes where there is maximum amplitude are known as antinodes. If I oscillate that string even more, I can create a different standing wave. For example, the following standing wave can also be created. This is a standing wave which instead has 3 nodes and 2 antinodes, 3 points on the string that are not moving, and 2 points that are moving with maximum amplitude. The number of nodes and antinodes that are created is fully dependent upon how fast I am moving that string, how much I'm oscillating it, and therefore what the frequency of the string is. Finally, it is natural to consider what the relationship is between the length of the string and the wavelength of the standing wave. For example, for the first standing wave, the wavelength is simply twice the length. We can see this by virtually extending this string such that it is the same length as a wavelength. Doing this, it is clear that the length of the string is simply equal to half of the wavelength. Capital L is equal to lambda divided by 2. In the second example, it is pretty clear that the length of the string is simply equal to the wavelength. In other words, capital L is equal to lambda. The first type of standing wave is in fact known as the first harmonic. The second type of standing wave is known as a second harmonic, and so on. We can continue this series by increasing the oscillations of that standing wave. In general, the wavelength of the nth harmonic is simply equal to twice the length of the string divided by n, divided by the number of the harmonic. There is also a very important equation associated with waves, which relates the velocity of the wave, the frequency of the wave, and the wavelength of the wave. This is v is equal to f multiplied by lambda. The velocity of the wave is simply equal to its frequency multiplied by its wavelength. Therefore, putting these two equations together also tells us the frequency of the nth harmonic. The frequency of the nth harmonic is simply equal to n, the number of the harmonic, multiplied by the speed of the wave, divided by twice the length of the string. Because of this, the first harmonic is also sometimes known as the fundamental frequency. This is because it is the lowest frequency of a standing wave that can be supported in a given length of string. The next harmonic, known as the second harmonic, is also sometimes known as the first overtone. It is the first overtone because it is the first harmonic above the fundamental frequency. Overall, all these possible standing waves that can be set up in a particular string is known as the harmonic series. One final tip for your MCAT is to know that if you wish to calculate what harmonic it is for a string, simply look at the number of antinodes. The number of antinodes tells you what the harmonic is. For example, if you go back and look at the two examples I gave you, in the first harmonic there was only one antinode. The string did not move at either end, and there was only maximum oscillation in the middle, therefore there was only one antinode. For the second standing wave, there was 3 nodes but only 2 antinodes. Since there was 2 antinodes, we know that that is the second harmonic. Standing waves can also be created using sound waves in, for example, pipes. There are of course many musical instruments that can be treated as sound waves traveling through a pipe. For example, something like a flute. The types of standing waves that are created are dependent upon whether the end of the pipe is open or closed, whether there is a wall or not at the end. To begin, let us consider pipes that are open at both ends. These pipes are simply known as open pipes. In general, antinodes are found at open ends and nodes are found at closed ends. Therefore, for open pipes, there is going to be antinodes at both ends, areas of maximum amplitude, maximum oscillation. Again, an example of an open pipe is a flute, a pipe that is open at both ends. Since an open pipe must have antinodes at both ends, the simplest possible standing wave in an open pipe is one in which there is only one node in the middle, as I've drawn here. Hopefully it is clear that the length of this pipe is simply equal to half the wavelength of the standing wave. If we were to extend this wave, we would see that its wavelength would be twice that of the pipe length. The next simplest standing wave we can put in this open pipe is as I have drawn here. In this case, we have 3 antinodes, one at each end and one in the middle, and 2 nodes, one node to the left and one node to the right of that antinode in the middle. Again, I hope it is clear, the length of this pipe is simply equal to the wavelength of the standing wave. A final example is the next standing wave, the next simplest standing wave that can exist in this open pipe. In this case, there are now 4 antinodes, 4 areas of maximum amplitude, and now 3 nodes, 3 points at which the standing wave is not moving. Again, I hope you're comfortable with seeing that the length of this pipe is equal to 3/2 of the wavelength of the standing wave. Hopefully you can see from these examples that it appears that the pattern is the same as that of standing waves in a string. Indeed, this is the case. The relationships between the wavelength, the length, and the frequency are the same as we introduced with strings. An open pipe has the same harmonic series as that of a string. A closed pipe, on the other hand, remember, has one closed end. As I stated, at a closed end, we instead expect a node, a point at which the standing wave is not moving. As we must have an antinode at the other end because it is open, the simplest standing wave in this case is as I have drawn here. Hopefully it is clear from this diagram that the length of the pipe is 1/4 of the wavelength of the standing wave. We would have to extend this wave 4 times until it repeats back on itself. Continuing on, the next simplest standing wave, where we have a node on the left and an antinode on the right, is as follows. In this case, the length of the pipe is simply 3/4 that of the wavelength. Finally, the next simplest standing wave for a closed pipe is as follows. Again, we must have a node on the left and an antinode on the right, and we can't have the two examples we have already given. This makes the third simplest standing wave, this as I have drawn. In this case, the length of the pipe is equal to 5/4 that of the wavelength. Hopefully you can see that we have one wavelength in the pipe and then 1/4 of the wavelength on the right. For an open pipe, it is pretty clear it does not have the same harmonic series as that of an open pipe or a string. Instead, the general rules are as follows. The wavelength of the nth standing wave is equal to 4 times the length of the pipe divided by the harmonic number. Using our relationship before, v is equal to f multiplied by lambda, velocity is equal to frequency multiplied by wavelength, we get that the frequency of the nth standing wave is equal to the nth harmonic n multiplied by the velocity of the wave divided by 4 multiplied by the length of the pipe. Remember, when dealing with pipes, we are now dealing with sound waves. Therefore, on the MCAT, you could be, for example, given one of these diagrams and asked to find the frequency. You would have to use the fact that you know that the speed must be simply the speed of sound, 343 meters per second in the case when it is air at 20 degrees Celsius. I would now like to finish this discussion on sound by considering a useful application of sound waves, namely ultrasound. Recall from a previous slide that I stated that the ear is sensitive in a frequency range from 20 Hz to 20,000 Hz. Any sound waves above 20,000 Hz are known as ultrasonic waves. Such waves are used in medical imagery, for example to visualize organs and anatomy. How ultrasound waves are in fact used is as follows. Ultrasonic waves are first emitted by a transmitter and focused towards a particular part of the body. These waves are then reflected by that part of the body, for example an organ, back towards the same transmitter. As we know the speed of the wave, the frequency of the wave, and the total time taken for that wave to travel, we can calculate how far in that particular part of the body is. This information can then be used pictorially to create a representation of the anatomy. A more complicated version of an ultrasound, known as a Doppler ultrasound, is considered in one of the sample passages we have provided for you. A Doppler ultrasound is used to determine the speed of a fluid within the body, for example blood flow. This is done by detecting the frequency change of the reflected sound waves. In the next video, we shall consider a different type of physical wave, namely a light wave. Before moving on to this, let us first check that we understand the principles that I've introduced in this video about sound waves. The first question is testing our knowledge about the speed of sound. It is asking us in which of the following substances does sound propagate through the slowest. Is it a low-density gas, a low-density solid, a high-density gas, or a high-density solid? Well, recall that the speed of sound through a particular medium is equal to the square root of the bulk modulus capital B of that medium divided by the density rho of the same medium. Therefore, straight away, as speed is inversely proportional to the square root of density, we know that the speed will be slowest for a greater density. Therefore, the answers must be C or D. I also stated that the bulk modulus is greatest for a solid and smallest for a gas. Therefore, since speed is directly proportional to the square root of bulk modulus, the speed will be lowest for a gas. Therefore, overall, the speed is going to be smallest for a high density gas. Therefore, the correct answer is option C. This next question is making sure we feel comfortable with going from sound intensity to sound level. Remember, sound intensity had a very large scale, so I introduced a logarithmic scale known as sound level to deal with this so that we do not have to deal with very big or very small numbers. The question is asking us what the intensity of a sound wave is that corresponds to a decibel level of 120. The sound level is 120 decibels. Is it 1 watt per meter squared, 10 to the 4 watts per meter squared, 10 to the 12 watts per meter squared, or 10 to the 24 watts per meter squared? To calculate this, let us write down the equation that relates sound level to sound intensity. The sound level in decibels beta is equal to 10 times the log of the sound intensity capital I divided by I sub 0. Remember, I sub 0 is the threshold intensity. It is the softest sound intensity our ears can perceive, and it is equal to 10 to the minus 12 watts per meter squared. Therefore, plugging in what we know, the sound level beta is equal to 120, which is equal to 10 times the log of the sound intensity, what we're looking for, divided by I sub 0, divided by this 10 to the minus 12 watts per meter squared. This is now one equation with one unknown, and therefore it can be solved. Hopefully you are comfortable dealing with logs, but if not, I will go through this step by step. The first thing we can naturally do is divide both sides by 10 to get rid of that 10 on the right hand side. Doing so reduces the 120 to 12 and gets rid of the 10 on the right. Therefore, we are left with 12 is equal to log I over 10 to the minus 12. To get rid of the log, I'm going to take 10 to the power of each side. Taking 10 to the power of a log is going to get rid of that log. Therefore, the left-hand side, remember, was 12 and now is 10 to the 12. And the right-hand side is going to be 10 to the log of something, which is just that something. It is just I divided by 10 to the minus 12. This can now be rearranged to give I is equal to 10 to the 12 multiplied by 10 to the minus 12, or simply 1. The sound intensity is equal to 1 watt per meter squared. This means that if you are told that the sound level is 120 decibels, then that sound has a power of 1 watt per meter squared. Remembering that power is energy per time, 120 decibels corresponds to a sound wave that has 1 joule of energy per square meter per unit of time, per second. Thus, the correct answer in this case is option A. The next question is dealing with standing waves that we just talked about, in this case in a closed pipe. For such a closed pipe, which has a length of 30 centimeters, what is the wavelength needed to create the second harmonic? Is it 15, 30, 40, or 60 centimeters? To answer this, we need to recall how the wavelength of the standing wave is related to the length of a closed pipe. Remember, a closed pipe has one end closed and the other end opened. It does not have the same harmonic series as that of a string. A string and an open pipe share the same harmonic series. The equation for a closed pipe is instead the wavelength of the standing wave lambda is equal to 4 multiplied by the length of the closed pipe capital L divided by the harmonic number n. Therefore, lambda is equal to 4 multiplied by the length of the pipe, which in this case is 30. I'm not converting this to meters because we also want our answer in centimeters, so I can simply leave this as 30 divided by the harmonic number n, which in this case is 2. We are told that we are looking for the second harmonic. Working this out, we get that the wavelength of the standing wave is 60 centimeters. Therefore, the correct answer is option D. This final question has to do with Doppler shifts. Remember, the emitted frequency from a source is not necessarily the same as the detected frequency. If either the source or the detector is moving, for example, if an ambulance and or the person listening to that ambulance is moving, then the detected frequency is going to be different than the emitted frequency. In this particular example, we are told that an ambulance is traveling at 126 kilometers per hour. It is emitting a siren of frequency 610 Hz. We are then asked what is the frequency heard by a pedestrian as the ambulance is approaching them. Is it 550, 590, 610 or 680 Hz? To work this out, let us write down our general equation for Doppler shifts. The detected frequency f prime is equal to the emitted frequency f multiplied by some factor. This factor depends upon the velocity of the wave, the velocity of the detector, and the velocity of the source. It is given by the velocity of the wave, simply v, plus or minus the velocity of the detector, divided by, again, that same velocity of the wave v, plus or minus, this time the velocity of the source. In this example, the detector is simply the pedestrian. As we are not told that this pedestrian is moving, we may assume that he or she is stationary and therefore the velocity of the detector is 0. What about the source? Well, the source is simply the ambulance. We are told that the ambulance is moving at 126 kilometers per hour. In this case here, we do have to be careful with units. Our frequency is stated as 610 Hz. Remember, a Hertz is simply a per second. As our frequency is in per seconds, we must make sure that our velocity also has seconds and not hours in it. Therefore, we need to convert kilometers per hour into meters per second. 126 kilometers per hour is equal to 126. A kilometer is 1,000 meters, so we multiply by 1,000, and then we divide by whatever an hour is in seconds. An hour has 60 minutes, and each minute has 60 seconds, so therefore 1 hour is 60 multiplied by 60 seconds. Working this out, we get that 126 kilometers per hour is exactly 35 meters per second. Now we are good to go to use our equation for Doppler shift. The detected frequency f prime, what we're looking for, is equal to the emitted frequency, which in this case is 610 Hz, multiplied by the velocity of the sound wave, which I have taken here as 340 meters per second, and you will be told what value to take in the question, divided by that same speed, 340, plus or minus the speed of the source. Remembering from my example that if the source is approaching the detector, we take the negative sign, then we do minus the speed of the source, and we just worked out that this source is traveling at 35 meters per second. Therefore, we get the speed of sound 340 minus the speed of the source, minus 35. 340 minus 35 is simply 305, and therefore we have 610 multiplied by 34 divided by 305. 610 is of course simply twice that of 305, and therefore we just get 2 multiplied by 340. The detected frequency is simply 680 Hz, and therefore the correct answer is option D. As always, let us now recap what we learned in this long video about sound waves. I began by reminding you that sound waves are a type of longitudinal wave. Their direction of oscillation is parallel to the direction of propagation. Then I described how sound waves are actually produced. Sound waves are simply mechanical disturbances in a medium. They cause oscillations in the density of the medium, creating compression and rarefaction regions. Since sound waves require particles to be created, sound waves can travel through liquids, solids and gases, but not vacuums. Vacuums not having particles therefore means that sound waves cannot travel through them. Again, as we shall see in the next video, light waves are instead associated with the electromagnetic field and therefore can travel through a vacuum, travel through a space without any particles. Next, as I just reminded you with a question, the speed of sound in a medium is dependent upon both the bulk modulus of that medium and the medium's density. In air at roughly 20 degrees Celsius, the speed of sound is equal to roughly 343 meters per second. Again, as we just saw in a question, the speed of sound is fastest in a low density solid and slowest in a high density gas. Different frequencies of sound are detected by our ears as a difference in pitch. Our ears are only sensitive to a certain frequency and pitch range, namely from 20 Hz to 20,000 Hz. Any waves below 20 Hz are known as infrasonic waves, and any waves above 20,000 Hz are known as ultrasonic waves. As I just reminded you about in a question, the Doppler effect is the fact that the detected frequency is different from the emitted frequency if either or both the detector or the source is moving. Shock waves are a special example of the Doppler effect and are created when the source is moving at or above the speed of sound. Sound intensity was then defined as the average rate of energy transfer per unit area. In other words, it is the power of the sound waves per unit area. I also stated that the sound intensity is proportional to the square of the amplitude of the wave and inversely proportional to the distance from the source. As sound intensity has such a very large range, I then introduced a logarithmic scale so that we don't have to deal with such large or small numbers. This scale is known as sound level and is measured in decibels. One thing I did not mention about sound that can come up on the MCAT is what is known as sound attenuation. As I just stated, sound intensity decreases with the square of the distance from the source. However, this is not the only reason sound intensity can diminish. Sound intensity also diminishes because of what is known as attenuation or sound damping. Sound attenuation is the gradual loss of sound due to non-conservative forces such as friction. Remember, sound waves have an energy and power associated with them, and as they travel through a medium, non-conservative forces can take some of that energy away from the waves, thereby decreasing their sound intensity. This causes the amplitude of the wave to decrease. Remembering that intensity is proportional to amplitude squared, any change in amplitude is also going to cause a change in sound intensity. However, intensity is not related to frequency, and therefore the frequency of the wave does not change due to damping. Going back to the video, I then discussed what happens when two waves interact with each other when there is wave interference. If these two waves are in phase with each other, there is constructive interference, and if they are totally out of phase with each other, there is destructive interference. In general, however, there is usually partially constructive or partially destructive interference for waves that are somewhat out of phase with each other. One natural phenomenon associated with wave interference is that of standing waves. These waves are created by a transmitted wave and a reflected wave interfering with each other. Such waves can be created in many different situations, for example on strings or in pipes. As I emphasized, such standing waves are closely related with the length of either the string or the pipe. As I stated, the resulting harmonic series for a string is the same as that of an open pipe. A closed pipe, on the other hand, has a distinct different harmonic series and therefore different equations that relate the wavelength of the wave and the length of the pipe. I then wrapped up this video by introducing a useful application of sound waves known as ultrasound. Ultrasound uses ultrasonic waves, in other words sound waves with frequency greater than 20,000 Hz, to create images of anatomy. It does this by firing sound waves at a particular part of the body, then detecting the resulting reflected waves. As we know all the properties of these waves, we can then use this information to calculate the distance from the detector to that part of the anatomy, thereby creating a visual image of that part of the anatomy. Such images can then be used to find or detect any unusual anomalies associated with that part of the body. As I've stated many times, in the next video we're going to look at a different physical wave, namely a light wave. As this is again another example of a wave, please be sure that you are comfortable with looking at this physical wave before moving on to another type of physical wave. As always, I hope this video has been useful to you, and I shall see you guys in the next one.